Good morning all. Today we are going to study about the topic transmission line capacitance. Capacitance in a transmission line is due to the potential difference between the conductors. In transmission line, the conductors acts as parallel plates and air acts as the dielectric medium of the capacitor. Since the capacitance is proportional to the length of the transmission line, their effect is negligible when the length of the transmission line is less than 80 km, or in the case of low voltage transmission line. Whereas in the case of high voltage and long lines, this capacitance parameter is one of the most important one. Just like we have considered magnetic flux linkage in inductance parameter of transmission line, here we have to consider electric potential. It is because basically capacitance is defined as charge per unit potential. Hence the concept of electric potential is very important for the determination of capacitance parameter in transmission lines. Electric potential is defined as the work done in moving a unit positive charge from infinitive to a particular point against the electrostatic force of the field. That is a basic definition of electric potential which you have studied during your 11th and 12th standards. According to the Gauss Law, the surface integral of electric flux density, which is indicated as D. So according to the Gauss Law, the surface integral of electric flux density around any closed path is equal to the net charge enclosed. In this relation, the D can be replaced by epsilon E, where epsilon represents the permittivity and E indicates the electric field intensity. D is representing the electric flux density. So the relation between D and E is D is equal to epsilon E. Hence, for D we can substitute epsilon into E. So the Gauss law can be written in this form also. We will begin with potential at a point due to a single current carrying conductor. Here the single current carrying conductor is having radius r, and we are going to find the potential at point P, which is at a distance x meters from the center of the conductor. In order to calculate the value of potential at point P, we will consider a Gaussian surface. In this case, the Gaussian surface will be a cylinder having radius x. The electric field is always radial in nature. There will not exist any tangential component. Then using the Gauss law, we can write the relation closed surface integral of epsilon E dx is equal to q enclosed. As we have considered the Gaussian surface as a cylindrical one having unit length, therefore its surface area, closed surface area, can be represented by 2 pi x into 1. Hence the Gauss law can be written as epsilon 0 Ex 2 pi x into 1 is equal to the net charge enclosed. Please note down, epsilon 0 Ex 2 pi x into 1 is equal to the net charge enclosed, that is Qa. The epsilon term has been replaced by epsilon 0 due to the presence of free space in the Gaussian surface. Now from that relation we can easily write the relation for E, that is electric field intensity, as Qa by 2 pi epsilon 0 x. In this relation, if you see, when the value of x is approaching infinity, then the value of E becomes 0. Hence we can consider that at infinity distance apart, there exists a neutral plane where the value of electric field intensity is actually 0. That is, we can say that at the value of x is equal to infinity, there exists a neutral plane. Now let's find the potential difference between the surface of this conductor and the neutral plane which is situated at the infinity. That can be easily found out by integrating the value of electric field intensity from surface to infinity. That is, integrating it from r to infinity, taking Qa by 2 pi epsilon 0 outside the integral. So actually this potential at A is defined as the potential difference between the surface of the conductor and the neutral plane which is located at the infinite distance apart. Now let's see potential at a conductor due to a group of charged conductors. Here in this diagram you will be able to see numerous conductors, that is conductor A to conductor F. We are going to find the potential at conductor A due to the influence of charges which are flowing through all the other conductors. First we will write down the relation of potential at A due to its own charge. This one we have just derived now, that is r to infinity Qa by 2 pi x epsilon 0 dx. Next we will find out the potential at point A due to charge which is flowing through this conductor B, that is Qb. This is very much similar to the external flux linkage which we have considered during the study of inductance of transmission lines. We won't be taken into consideration the electric flux which is existing in between this. So in order to find the potential at A due to the charge which is flowing through this conductor, that is QB, we will be taking the integration from D1 to infinity QB by 2 pi epsilon 0x. Similarly, we can find the potential at point A due to the charge which is flowing through this conductor CS, taking the limits of integration from D2 to infinity. Similarly, while considering the effect of conductor D, that is potential at A due to the charge which is flowing through this conductor, we will be integrating the limit from d5 to infinity, and the charge value will be QD. So similarly, we will be able to calculate the potential at point A or the potential at conductor A due to the influence of all other conductors, and we can write the overall potential at conductor A as taking the sum of all this. Now taking 1 by 2 pi epsilon 0 common from all these terms, we will be able to write QA natural log of 1 by R plus QB natural log of 1 by D1, like that. And taking the natural log of infinity term common, we will be getting inside the bracket QA plus QB plus QZ. Taking natural log of infinity common, we will be able to get QA plus QB plus QC up till QF. Considering the system to be a balanced one, then the charges, the sum of the charges which is flowing through all these conductors will be equal to 0. Hence we can neglect this term and we are left with 1 by 2 pi epsilon 0 QA natural log of 1 by R plus QB natural log of 1 by D1, like that up till natural log of 1 by D5. So this is how we have find out, or we have determined, the potential difference between conductor A and neutral plane at infinity due to the influence of a group of some other charged conductors. Now let's move to the capacitance of single phase overhead transmission line. This is actually a single phase system. This diagram is indicating a single phase system. You are quite familiar with this diagram because you have studied them in the derivation of inductance of transmission line in the case of single phase system. So there will be two conductors. One will be carrying the positive charge and the other will be carrying the negative charge, as this will be the return path. And both these conductors are separated by a distance small d, and each of these conductors are having radius small r. Now we are going to find the potential at point A, or the potential at conductor A. There exists the potential due to its own charge and the potential due to the charge which is flowing through this conductor B. So we can write the potential difference between conductor A and infinite neutral plane as integral r to infinity q A. QA is actually q divided by 2 pi epsilon 0x dx plus integral d to infinity, that is due to the influence of charge which is flowing through conductor B, which is actually minus q. So integral d to infinity minus q by 2 pi epsilon 0 x dx. Taking q by 2 pi epsilon 0 common from it, we will be able to write the relation in the bracket as natural log of infinity by r minus natural log of infinity by d. Further simplifying it using the simplified logarithmic expressions, we will be able to write the relation as q by 2 pi epsilon 0 natural log of d by r. This is actually the potential difference between conductor A and the infinite neutral plane. Similarly, we can find the potential at point B, or the potential difference between conductor B and the infinite neutral plane. See, in the conductor B, there exists a potential due to its own charge and the potential due to the charge which is flowing through conductor A. So while taking minus q by 2 pi epsilon 0 common from that and simplifying it, we will be getting the relation of VB as minus q by 2 pi epsilon 0 natural log of d by r. In order to find the potential difference VAB, that is VA minus VB, you have to subtract this term with this term. Then you will be able to get the value of potential difference as 2q by 2 pi epsilon 0 natural log of d by r. Our aim is actually to find the capacitance of single phase overhead transmission line. The relation for capacitance, we know that C is equal to charge per unit potential, that is C is equal to Q by V. We have determined the potential difference which is existing between these two conductors. So we can easily find the value of capacitance CAB as Q by VAB. We have to substitute the value of VAB here. and then finally we will be able to get the capacitance of single phase overhead transmission line as pi epsilon 0 by natural log of d by r. You must by heart this relation, then only you will be able to solve the problem. Not only just by hearting this relation, you have to study the derivation also, because this derivation is very important. As both these conductors are carrying equal and opposite charges, definitely the potential at the midpoint will be 0. Hence we can consider a neutral point at the midpoint. Then therefore the CAB can be considered as the series combination of CAN and CBN. Unlike the case of resistors, when two equal capacitors, suppose when two equal capacitors of capacitance value C are connected in series, then their effective value of capacitance is C by 2. Here we know the resultant capacitance is actually CAB. Therefore the capacitance, that is this each capacitance, can be represented as 2CAB. Hope it's clear for you. Therefore this capacitance neutral, that is CAN as well as CBN, both are same and they can be indicated by a common term, that is CN, which is actually 2 times CAB, and the value of CAB we have already determined as pi epsilon 0 by natural log of natural log of d by r. Therefore we can write CN as 2 pi epsilon 0 natural log of d by r. So far we have considered the capacitance of single phase overhead transmission line. In the case of a single phase system, we have considered the capacitance from conductor A to conductor B, which we had written as CAB, and its value was pi epsilon 0 by natural log of d by r. While coming to the case of three-phase overhead transmission line, we are not going to determine the capacitance from conductor to conductor. Rather, we will be identifying, or we will be determining the capacitance of each conductor. First, we will begin with symmetrical spacing. Just like we have considered in the case of inductance of transmission line, here also in the case of three-phase system, there are two cases, that is symmetrical spacing and unsymmetrical spacing. So now let's see symmetrical spacing. In the case of symmetrical spacing, as you know, all these three conductors are placed at equal distances apart, which is represented here as d. We are going to find the capacitance of this conductor A. So in order to find the capacitance of this conductor A, we have to find the potential at this conductor. So the potential at this conductor A is due to its own charge, and then due to the charges which are flowing through this conductor B and conductor C. The charge which is flowing through each of these conductors is indicated as QA, QB and QC. So the potential at A can be written as the potential due to its own charge, that is R to infinity QA by 2 pi epsilon 0 x dx. Then potential due to charge QB, which can be represented by d to infinity QB by 2 pi epsilon 0 x. Similarly, the potential due to charge C also can be written. 1 by 2 pi epsilon 0 can be taken common. Then we will be writing the relation like this. Then from these two terms we can take natural log of 1 by d as common, and we can write it as QB plus QC, as we know that the system is a balanced one. Therefore QA plus QB plus QC is equal to 0. So from this relation, instead of QB plus QC, we can write it as minus QA. So the relation gets modified into this form. Further, taking QA common from these two terms, we will be able to write the relation for potential at this conductor A as QA by 2 pi epsilon 0 natural log of d by r. Now we can find the capacitance of conductor A by dividing QA with VA. The value of VA is determined as QA by 2 pi epsilon 0 natural log of d by r. We have to divide it with QA. Then we will be able to get the value of capacitance of this conductor A as 2 pi epsilon 0 natural log of d by r. This relation is same as that of the capacitance to neutral in the case of a single phase overhead transmission line. So far we have seen the symmetrical spacing case in the case of a three-phase system. Next we are going to consider the unsymmetrical spacing. As we all know, in the case of unsymmetrical spacing, definitely the phenomena of transposition comes into occurrence. That is, the position of conductors are interchanged at equal intervals in such a way that each conductor occupies the position of other one over an equal distance. As we are going to find the capacitance of conductor A, we have to first obtain the potential of this conductor A. In order to find the potential of this conductor A, we have to find the potential of this conductor at this position, then at this position, and then at this position. That is, we are determining here. Potential at first position is indicated as V1, and second position is indicated as V2, and third position is indicated as V3. So we have to find the potential at this first position, that is potential of this conductor A at this position. It can be easily determined by using the relation 1 by 2 pi epsilon 0 qa natural log of 1 by r. That is the potential due to its own charge. Then next the potential due to the charge which is flowing through this conductor B, which is written as 1 by 2 pi epsilon 0 qb natural log of 1 by d3. Then due to the charge which is flowing through this conductor C can be written as 1 by 2 pi epsilon 0 qc natural log of 1 by d2. Now all of you might feel a doubt that one infinitive term also must exist here. In real practice this infinitive term is also existing there, but if you are taking natural log of infinitive common from all these three terms, then in the bracket you will be getting the term qa plus qb plus qc. Considering the system to be a balanced one, qa plus qb plus qc will be equal to 0, hence natural log of infinitive term does not exist. Similarly, we can find the potential of this conductor A at the second position and then potential at third position. Once after finding the potentials at these 3 points of this conductor A, we can write the average potential of this conductor as 1 by 3 into V1 plus V2 plus V3. Now taking 1 by 2 pi epsilon 0 common from them, and while adding these three terms, if you are taking QB common from them, we will be getting inside the bracket the term natural log of 1 by d1 d2 d3. Similarly, if you are adding these three terms while taking QC common from that, then you will be getting inside the bracket natural log of 1 by d1 d2 d3. Now further taking in natural log of 1 by d1 d2 d3 common from these two terms, we will be able to get it as qb plus qc inside the bracket, which can further be written as minus qa, and this term can be written as 6 pi epsilon 0. So now the relation for potential of conductor A can be written as 1 by 6 pi epsilon 0 qa natural log of 1 by r cube minus qa natural log of 1 by d1 d2 d3. While simplifying it further using the logarithmic expression, we can write this as qa by 6 pi epsilon 0 natural log of d1 d2 d3 by r cube. Taking 1 by 3 common from it and then taking this 1 by 3 inside this natural log term, we can write the relation as qa by 2 pi epsilon 0 natural log of d1 d2 d3 raised to 1 by 3 by r. This is actually cube root of d1 d2 d3 by r. So this is how you get the relation for potential at A, or the potential difference between the conductor A and neutral plane in the case of a three-phase transposed system. Now you can easily find the capacitance value by simply dividing QA with VA, and the value of VA you have found out here. Now you can just simply divide it with QA, and then you will be getting the relation as 2 pi epsilon 0 divided by natural log of cube root of d1 d2 d3 by r. You must remember this relation also, then only you will be able to solve the problems associated with this. Now let's see some numerical problems. In the first problem, you are asked to find the capacitance of a single phase two-way system. All parameters are given directly. Since you are asked to find the capacitance of line per kilometer, you have to find the value of CAB, that is pi epsilon 0 by natural log of d by r. As I told you, in the case of a single phase system, we will be finding the value of CAB, whereas while coming to the three-phase system, we will be finding the value of CA. Here you are asked to calculate the capacitance of each line conductor per kilometer, that is you have to find the value of CA. It's actually a problem based on symmetrical spacing, so you can easily find the value of capacitance by using the relation 2 pi epsilon 0 by natural log of d by r. Now moving to the third problem. This is a case of unsymmetrical spacing, so you have to use the relation 2 pi epsilon 0 by natural log of cube root of d1 d2 d3 by r. You have to find the value of cube root of d1 d2 d3. All these parameters are given, and then you have to make that substitution here, and then you will be able to get the value of CA. But in this problem you are asked to find not only that, you are asked to find the charging current per phase. By using this relation, we will be able to identify only the capacitance per unit meter. If you see in this problem, the line length is 100 kilometer. Therefore, you can find the capacitance value for this 100 kilometer by multiplying it with 100. Now let's see how to identify the charging current. In the case of a capacitor, the charging current is identified by using the relation IC. IC is actually the charging current. IC is equal to voltage divided by XC, where XC is actually the capacitive reactance and the relation for capacitive reactance is 1 by omega C. So we will be able to write the relation for IC as omega C into V phase, that is voltage. Omega's value can be easily identified by using the relation 2 pi into 50. Cn's value we have calculated, and V phase, in this problem the value, that is 132 kilovolt, this particular value is actually indicating the line voltage. It's not mentioned whether it is a star connected or delta connected system, nothing is mentioned. So by default you have to consider the system as a star connection one. So for V phase, in the case of a star connected system, the relation between line voltage and phase voltage is V phase is equal to line voltage by root 3. Always in the problem, if it's not specifically mentioned that the voltage value given is phase voltage, by default you have to consider it as line voltage. Then you will be able to find the value of phase voltage from this by dividing it with root 3. So once after determining the value of V phase, Cn, and knowing the value of omega, you can easily calculate the value of charging current. I will just once again say about the relation for this charging current. In the case of a capacitor, the charging current can be written by using the relation voltage divided by capacitive reactance, and the relation for the denominator term, that is capacitive reactance, is 1 by omega C. So the relation for charging current will be voltage divided by 1 by omega C. So you can take the reciprocal of the denominator and multiply it with the numerator, then the relation for charging current becomes IC is equal to V into omega C. That relation we are using it here to find the answer. With that we are completing today's session. In the next class we will see the topic bundled conductors.